This week it's our pleasure to have Leonid Polterovich, who will speak about contact topology meets thermodynamics.
Thank you very much for this opportunity. So indeed, I will talk about some works with Mikhail Entov, Lenya Ryzhik. And let me say a couple of words. What is this lecture about? So it was known already to Gibbs that one can think about classical thermodynamics in a kind of phase space which is equipped with the preferred form, one form, and we know about this one form, contact form. And the fact that it's contact form, of course, matters. So it's also kind of a textbook material that equilibrium of thermodynamical systems can be represented as Legendrian submanifolds. We will define everything. And here are some findings. So what we want to explain that in the if in the thermodynamic limits, so when you have some particle system and the number of particles becomes large, there is a phase transition. So then the corresponding Legendrian is not smooth. And that's basically, so what I want to say, it's almost tautology, okay? And for years I was asking young people doing C0, symplectic and contact topology is a trendy subject. Yeah, so how to extend symplectic rigidity to continuous objects. Okay, so do they have kind of good example in mind? I think that it was kind of unknown, so this is really naturally appearing of non-smooth object in the physical problem. So, second finding, it's the following, that rep chords, so trajectories of rep vector field joining Legendrian submanifolds can be under certain circumstances also in thermodynamic limit to be interpreted as kind of ultra-fast or instantaneous relaxation processes of non-equilibrium thermodynamics. And this I will explain. It's one of the things.
Could I ask you a question? You say a phase transition of the first kind, you mean it's a first order transition, or do you count second order transitions?
So I mean the following, that if you write down free energy as function of let's say external parameter, yeah, so it is continuous but not smooth. Okay, so that's exactly kind of, you will see that's almost tautologically, or just tautologically. This means that in the limit you get not smooth. Okay, and so these chords correspond to certain classes of processes, and this I will explain. And the second thing, which is kind of is not really written yet, but I mean it's under constructions. So there is another trendy topic in quantum topology, so partial order on the space of Legendrian submanifolds. So it appears in non-equilibrium thermodynamics and governs slow process. Yeah, so that's basically what I want to explain. So let me just remind that it's a kind of prologue, so some contact preliminaries. So we will work in very specific contact manifold. It's a jet bundle to a given manifold, so it's just product of cotangent bundle in real numbers with this form dz minus pdq. So by definition, contact structure is a kernel of this form, so it's space of kind of hyperplanes, right? And the Legendrian submanifolds are those who are tangent. Okay, so, and the rep vector field for this form is just vertical vector field dpdz. Okay, so we will say that two disjoint Legendrians, so Legendrian means, as I said, that lambda vanishes on the tangent space, so they interlinked if the following holds, that if you have a positive kind of contact Hamiltonian, so then there exists a chord, there exists a trajectory which starts on one Legendrian and ends on another Legendrian. Okay, and we say that interlinking is robust if lambda 1 prime is Legendrian isotopic to lambda 1 outside lambda 0, so then these two guys are still interlinked, but probably with different mu. So this number mu actually governs the length, the time length of the chord. So we usually want to have some uniform bound on the length of the chord, which of course depends on lower bound on the Hamiltonian. Okay, and we'll say that the chord is non-degenerate if image of one Legendrian under this piece of rep flow is kind of together with the image of tangents plane to another Legendrian generate the whole tangent hyperplane. Okay, so basically the picture which you should have in mind, so we have two Legendrians and we are looking for a core trajectory which starts on one Legendrian and ends on another Legendrian. So that's the central object, one of the central objects of contact geometry by 1001 reasons, so in Riemannian geometry. So, okay, so now still about interlinking. So here is a theorem that if we have a Legendrian which is Legendrian isotopic to the zero section, and assume that there is a kind of unique chord which starts on lambda 0 and ends on lambda 1. Okay, so then these two things are interlinked necessarily. Okay, so then does not matter, you can switch on any positive Hamiltonian, you will still get a chord. Okay. And this is a technologically non-trivial result. It involves Legendrian contact homology and some results on persistence models, barcodes in the framework of Legendrian contact homology, and finally involves Poisson-Brecht invariance. Somehow the proof probably is not optimal, but is optimized for the to get the results. So that's how we can get the result. And here are some remarks. So this isotopy condition is important. So a result has otherwise counterexample. And there exists kind of, it's so to say, like first step towards interlinking. So there is more sophisticated criterion of interlinking by Rizal and Sullivan, which is based on more sophisticated persistence model. And since we introduced this notion, so there was some use of it by Maxim Stokich. So he used interlinking for the question like whether the C0 limit of Legendrians is Legendrian. So it's a kind of certain mathematical topic which is developing, and there was recently an interesting development. So, well. So to this end, I have to define partial order on Legendrians. So like probably 20 years ago, we defined partial order on the group of contact diffeomorphisms, right? So contactomorphisms of a contact manifold. So these are kind of paths of contactomorphisms which are generated by positive Hamiltonians, which means that the trajectory of each point kind of is transversal to contact structure in the positive direction. Okay, and then there is the whole question whether it's partial order or not. So there are orderable manifolds, non-orderable manifolds. So then this was generalized to Legendrians by Chernov and Nemirovsky, and we say that convexly supported part of Legendrians is non-negative if it's generated by vector fields on which this contact form is non-negative. Okay, so we're kind of going to positive direction. And again, you can, if such path exists, so you consider this binary relation lambda 0 less or equal than lambda 1. And the difficult question is whether it's a kind of Ginian partial order. So Ginian partial order means, of course, that if A is less or equal than B and B is less or equal than A, so is it true that A can say that? Okay. So all other axioms are trivial. Okay, and for Legendrians, there are orderable classes and non-orderable classes, but apparently it's known that the class of zero section in this kind of jet bundle, so in our main example, is orderable. So this was proved by Chernov and Nemirovsky and by Kalin-Ferrand Pushkari. And a very nice theorem by Alois and Arlov states that if we have disjoint submanifolds lambda 0 and lambda 1 in this class, lambda 0 is less or equal than lambda 1, that they are interlinked. Okay, so you can establish interlinking in this general. So that's basically the contact kind of characters which I'm using. So rep chords and partial order. So I will show how they enter into this discussion about thermodynamics. So that's the end of prologue. Any questions at this point? Okay. So now contact thermodynamics. So it's a little bit foreign setting for kind of symplectic audience, so to say. And so we start with the manifold with the volume form. So I think that in my talk, this manifold will be mostly a finite number of points, okay, or interval -1, 1. Okay, so this is not the contact manifold of interest. And we consider all possible positive probability densities on this manifold. Let's say, yeah, so positive integral equals to 1. And there is a Hamiltonian, which is a function on this manifold. So there is no symplectic structure. It's not a Hamiltonian in any kind of reasonable way. It depends on some parameters, on control parameters, so intensive parameters. I will give example very soon. Okay, deal mostly with one example in this talk, but so I just want to say that without this parameter, there is no story. So no intensive parameters, no contact. Okay. So you define entropy, and you define a functional which is called free energy. So it's a map which looks like this. So it's minus beta inverse times entropy. So entropy is usual integral rho ln rho d mu, and this is just average value of Hamiltonian. Okay, and beta is 1 over temperature, according to thermodynamic tradition. And one wants to solve the following variation problem. So one wants to find minimum of the free energy for rho over p and for fixed external parameter q. And it is well known that the solution is Gibbs distribution. So it looks like this. You take e in the power beta h normalized, so divided by this partition function integral over m in the power beta h d mu. And then because of the parameters, you can define kind of generalized pressure. So it is an extensive variable. So integral minus d phi dqi, which is integral over m dh d. Okay. So these are the main kind of objects. And now you do the following. So you consider thermodynamic phase space with the one form lambda dz minus p dq. So actually manifold x, which appeared earlier, is kind of standard problem. Okay. And so here is the idea. So idea due to Kim and O of 2022. So we can write use free energy as generating function of the equilibrium Legendre. So we can write this equation. So we consider all PQZ so that there exists rho, so that p d rho equals to 0, p equals to minus d of dq, z equals to minus v of qr. Okay. So somehow this is very, very well-known formula for kind of symplectic topologies. Just rho usually is element in some huge space Rn, or if you wish, in the space of loops, okay, parts. And then this is the standard kind of generating function. Okay. But here we do the following. So we consider as a generating function this rho, which is a measure kind of density. And so then what we do, we literally consider extremum of free energy. Okay. and bookkeep the value of energy and this generalized pressures for given external variable. Okay, so now what is relaxation problem? So I would say that until this point, there is absolutely no kind of discrepancy in what people think about quantum thermodynamics. Okay, so discrepancy starts here. So what is how to describe relaxation processes? And there are several schools. Okay, so just people which are doing different things, sometimes not so clear how they are related. So, but in any case, what we want to understand the following things. So we kind of perturb our system, so push it away from the equilibrium, and we want to understand how it returns to the equilibrium. So what are the laws which governs this? Okay, so there is a bunch of kind of papers by Braveti, De Leon, Goto, Grmela, Haslach, Mashkin, Rugala, Oettinger, van der Schaft in alphabetic order, which developed the following approach that these relaxation processes can be modeled by contact Hamiltonian systems, not necessarily kind of with positive contact Hamiltonian. So actually vice versa. So usually dissipative systems which kind of converge to equilibrium. And this is not the approach which I'm using in this paper, though of course we were very much influenced by it. So now let me start developing kind of these topics. One of the main questions of interest for me. So there is the following constraints on the process. So one can do some arithmetics, roughly speaking, with first and second laws of thermodynamics, which I skip. And one get to the following conclusion, so well-known kind of that if you have a kind of reversible process, so then lambda, so this contact form on tangent vectors to such process vanishes. So this is called the fundamental thermodynamic relation. And if you have a reversible process, so then lambda of gamma dot, I mean, the moment when you have non-trivial entropy production, so this is positive. So lambda of gamma dot is positive. Okay, so just believe me. So now there is what you can do. So I did not tell you what are these coordinates, but there is a sort of very distinguished pair of coordinates, temperature and entropy, and I can consider them within this thermodynamic space, so I can exclude them and consider temperature as parameter and just forget about entropy. So if they excluded, so we also assume that along the processes, temperature is not decreasing. Okay, so that's kind of what we have. Okay, so now first approach, and I think it's quite mainstream approach. So the principle, we return to equilibrium by minimizing this free energy. So then let's do the following. So we consider free energy, and we consider gradient equation associated to this free energy. So d rho dt equals to minus nabla phi with respect to certain metric, but metric where, so u is fixed, and we should consider metrics on rho. Okay, and there is a famous metric which is called Wasserstein metric, which if you would be, let's say, on a closed Riemannian manifold, so the formula is the following: you take rho dot kind of is a tangent vector to the space of densities, and you find unique function psi with zero mean, which solves this equation kind of rho dot equals to nabla rho. Nabla of divergence, right? So from nabla psi, and then you send this scalar product to be integral m nabla psi 1, nabla psi 2 rho mu. It's extremely ingenious construction due to okay, I believe due to Otto who brought this to this thermodynamic framework, and then you get a meaningful conclusion. Meaningful conclusion is that the gradient flow is a Fokker-Planck equation. So d rho dt equals to temperature time Laplacian plus drift. So you can think that there is diffusion and drift, right? So some dynamical system and diffusion, and this inverse temperature kind of governs it is coefficient of the diffusion. Okay, so that's what more or less physicists kind of think how this should converge to the equilibrium. Okay, and I want to emphasize that for us, this kind of equation is the following. So remember that this phi is a generating function. So actually, what symplectic topology is kind of how they view this equation. So we have a generating function phi of psi, and we solve equation psi equals to gradient phi with respect to psi. And this equation is famous in symplectic topology because if you, instead of kind of discrete variables, you will consider paths, you will get Cauchy-Riemann equation. Okay, well, it's completely a mysterious connection, which is, and we know this is true. Okay, so let's go further. I wish to, I mean, this was a kind of general theory, but what I want to do, I want to focus on more or less one model in which we spend kind of most of our time and effort, where you can kind of see something. Okay, so it's Curie-Weiss magnet kind of.
Could you go back to the previous slide?
Yes.
So these are flows where I start from a non-equilibrium measure and I flow to equilibrium measure, more or less the way you would with Monte Carlo, or this is just another flow, just different flow than Monte Carlo or Glauber.
Different flow from
Glauber or Monte Carlo or.
So that's yeah. So how we will do it? I will not probably arrive. Yeah, it's different but very related. And I think that one of the challenges of our paper with Entov and Ryzhik was to relate this.
But is this the flow that you're using with the Wasserstein metric?
Yeah. Okay. So here is answer to your question. So they are related. They are related in the following way that, let's say, for instance, drift of Fokker-Planck is related to this Glauber ODE, which you get kind of in the limit. But this should be proved, and I think that we have some result in this direction. It's probably not ultimate. Okay, so we probably cannot prove that really kind of honest dynamic is close. But what we do, in the limit, we can tune this remaining metric on which we build Wasserstein in such a way that indeed diffusions are the same, and so then drifts are related by diffusion. But that's yes, and so then the next question is, okay, so very good. So equations are similar, so then prove that dynamics are convergent. This we cannot do. This becomes technical and complicated and brings us. I mean, it is.
But you know that this one under generic circumstances will converge to. You know this gradient.
But yes. This will converge exactly as Glauber. It will converge to the same thing. So I want to say more. I want to say that actually this dynamical behavior is similar, okay. And I can say something about this, but not the final kind of. Okay, and yeah. So this was, and I will mention it. So at some point, and okay, you will see. Okay, so now we have this complete graph with n vertices. So you see, this is the graph. So in each graph sits spin up or spin down. So our state space is just space of functions of Gn to -1, 1. It's discrete space, and you can, I mean, for me, it's a manifold. Yeah, okay, fair enough. Okay, so now you have mean spin, it's just 1 over n sum sigma of J over such a configuration, something which takes values -1, -1 plus 2 over n, etc., 1 minus 2 over n, 1. And this is very important. So you have a segment -1, 1, and you consider it kind of discrete version. Okay. So then Hamiltonian looks like this. So the term Bm square over 2 is responsible for interaction between the spins. And this remarkable words, Curie-Weiss or mean field, means that each spin interacts with each spin. It's a baby example, still kind of beautiful and not totally trivial. Okay, and Q is magnetic field. So now we assume that in principle spins tend to align, right? So and when you include magnetic field, so if it's very, very negative, so spins kind of look to -1, it's very, very positive, spins look to +1, and what happens in the middle kind of God knows. Okay, and that's what we want to know. Okay, so that's the model, and now there is a remarkable observation that because this it's kind of again it's textbook, so nothing, no new insight on our side. So because everything depends on this magnetization, so let's reduce the state space. So instead of considering like 2 in the power capital N, you know, kind of all configurations. So let's just consider this set of points where magnetization takes place as our kind of state space, much smaller. Okay, and that's kind of very good. And after this reduction, so you can recalculate the Hamiltonian, and recalculate the entropy. So this is some calculation again from the textbook. So you get formula for free energy per particle. So note that n enters as a multiple everywhere. So we will do normalization all the time, and you get kind of interesting function which under certain values of parameters. So what is important for me, and I will stick mostly to this case, it's more difficult case when V beta is bigger than 1. Okay, so this free energy has like 1 maximum and 2 minimum. And 1 minimum is global, kind of 1 is local. Okay. So general pressure per particle for such models, I mean, you can calculate is just average mean spin, it's called magnetization. So my view, is the following. So you have this system of spins and you look at it as a little magnet, okay? This magnet is influenced by its internal vector field, and you want to know everything about magnets, average characteristic. Okay, so then we can write down equilibrium Legendre, so with the help of this generating function, I kind of get you an algorithm. And you get, roughly speaking, the following picture. Okay, so you get the following picture. So this is the equilibrium Legendrian for finite kind of n, which you have, and then you go to the limit and you get this thick. You get this thick, okay? And so let me do this a little bit more carefully. So when I pass to thermodynamic limit, right? So when n goes to infinity and I do normalization, I can reconstruct this green kind of parts of something, some Legendrian submanifold. And so then this Legendrian submanifold, as you see, is manifestly non-smooth. And B beta is bigger than 1. But then what you can do a rather hooliganic thing. You can analytically extend the submanifold. And you have a formula, it kind of contains very nice functions like tangent hyperbolic, arctangent. So you extend, you get a really nice Legendrian submanifold. So this is front projection to the plane ZQ. So this is what we call Lagrangian projection, right? Okay, and then you really can prove the following theorem that in these red things, which correspond to kind of Legendrians for finite n, so they honestly converge to this green submanifold, right? So they C0 can converge, so out of singularity they converge with derivatives. So this is really very good convergence, okay? And so I believe one can do the following, one can make the following statement. One can redefine gamma convergence, right? So, or Hofer convergence in the case of Legendrians. Okay, and so then just consider completion, and you see that this thermodynamic limit kind of, yeah, so is actually limit this metric, and it is non-smooth because we will manifestly see that it is non-smooth. Okay, and so where happens phase transition, so you can find it, you can see it here, right? So if you have Q, for instance, this Q, so you see that you have three equilibrium points responding to the same value of the parameter Q. So one green, one blue, one black. Okay. And so how they related to this graph kind of free energy. So roughly speaking, kind of green is most stable, right? So blue is also minimum, but not the global minimum. And black corresponds to maximum, which is at all unstable. Okay, so now we have the following, so we can make the following conclusion that in the thermodynamic limit, so we have this limiting Legendrian submanifold lambda infinity. So the limiting Gibbs distribution is concentrated on the green part. Okay, so this manifests phase transition of the first time, and this sequence of rescale Legendrians converges in very kind of precise sense, this limiting Legendrian submanifold. So now the blue and, I mean, if we really kind of stand on the grounds of equilibrium thermodynamics, so just we're interested only in Gibbs distribution. So then we see only green part. Okay. So either then we can, as mathematicians, apply analytic continuation, which is physically very clear procedure, or we can do something else. So here one of the miracles happens that blue part actually can be seen from non-equilibrium perspective. So maybe I will, and this is basically related to what you're asking, because it's what is called metastable part. This is the same metastability which exists in Glauber dynamics. Okay, so I will say a word about this probably later. Okay, so now I want to consider the following model. So assume that I have Curie-Weiss magnet with n spins with some interaction, and so imagine that we have the following jump. So temperature jumped from T0 to T1, and T1 is bigger than T0, and a magnetic field jumps from Q to Q plus A. So how we can analyze this jump, right? So what happened? So first of all, system was, let's say, initially in equilibrium with respect to all parameters. So then in the final state, so we are in the same probability distribution, right? So probability distribution cannot change. So what changed is the way how we calculate energy and so on. Okay, and then we start relaxing towards Gibbs distribution, but with new parameters, B beta 1 and Q plus A. And so let me write down F0 and F1 for initial and final states. So I already will incorporate Q plus A into this jump. So if you wish, I took initial Legendrian and moved it to the left by A. Okay, still a Legendrian here. So then I can really describe this relaxation in two steps. So first step is an instantaneous jump. Okay, so density rho zero of NQ, magnetization NQ remain constant, and free energy jumps. And then second step, so from this initial condition, we start this Fokker-Planck relaxation, and by general theory, we will arrive to the equilibrium. But there could be a incident. And incident could be as follows, that this kind of limiting distribution and this equilibrium, so the initial equilibrium and terminal equilibrium could coincide. They, of course, will never coincide for finite time, but they could coincide in the limit. And so then the conclusion would be that in the limit, second step is just void. So you have just this jump from one equilibrium to the same equilibrium, and you are done. Okay? So now it remains to make the following observation. So we started with this Legendrian submanifolds already with some rescaling. Okay, and in the limit we converge to this Curie-Weiss Legendrian. And in the limit, what happens? So either we have no phase transition, so it's kind of honest Legendrian, or we have only stable parts of this Legendrian, and kind of in three-dimensional space they are connected. This vertical segment, right? So to make it continuous. And points on these Legendrians correspond to have the following meaning. So actually in the thermodynamic limit, this Gibbs distribution concentrates over Dirac delta measures, which correspond to magnetization sitting on this Legendre. Okay, so when we, let's say, draw this picture kind of on the plane, that Q, yeah, so for given Q, okay, let me do it. So if we draw this picture on the plane PQ, so for given Q, limiting Gibbs distribution sits here, so it's this point. Okay, everywhere, I mean, unless Q equals to 0, then it's more complicated. Okay, so on a smooth point, you simply have a very good concentration. Okay, and so this means that if these two gadgets kind of have one yeah, so let's make an assumption, yes, that n is huge, so I will assume that for large n, Gibbs distribution is just limiting Gibbs distribution. So I will say the following thing, that this Hamiltonian, if f1 of q equals to f2 of q, so then actually we have instantaneous jump and that's it. No relaxation. And it should be maybe explained why I can assume that limiting magnetization actually sits on this graph, but the reason is that we consider Hamiltonians which are fine in Q, and so then you have this formula that P equals to integral of m rho I dq, and rho is a delta measure, so actually you sit in this, it should be phi of Q. Okay. So in our situation, we can conclude the following things. So consider initial Legendrian and the terminal Legendrian, and assume that there exists a chord joining stable parts of this Legendrian. So this intersection points is exactly the chord. So m0 of q equals to m1 of q. So kind of limiting magnetization for given q, for regional Q and for regional system and for terminal system can say. So this means that we have a record which corresponds to the instant relaxation. Okay.
So you're taking two different Hamiltonians with different, slightly different parameters, right?
Yes.
And you start, and then you want to run. So how is the dynamics running? You're going to flow to the new one?
No, I think that we're trying to, okay, so our picture of relaxation consists of two steps. So one step is some instantaneous jump, another is Fokker-Planck dynamics. Okay, and instantaneous jumps is.
So you impose that by hand, or yes?
Well, I would put it in the following way. So not that I impose this by hand, but that's the only way I can interpret how relaxation goes. So that's kind
So
of.
you start, but you're,
But
are you gonna be flowing to the original Hamiltonian or?
yes.
Okay,
Yes.
that's what.
Yeah, so again, okay, I think this is, I would say that this is most important kind of part of the talk, so to say. Okay, so we have the following relaxation. T0 goes to T1 and U goes to Q plus A. So I view it like this. So T, which is 1 over beta, is parameter in my system. So I have a kind of two Legendres, right? So this. Okay. So now what I'm doing with this shift? I'm thinking that there is a magnet and external magnetic field. So I just bring generator of magnetic field by hands and put it in the same room instantly. Yeah. So my magnetic field jumped from Q to Q plus A. So this means that I will consider, if this is Q direction, this graph shifted by A over Q. So somehow my original system is just Curie-Weiss for temperature T0. My terminal system is T1, is Curie-Weiss for temperature T1 shifted by A. Okay, very good. So now I'm open to any suggestion. So what happens with my system? It's completely kind of experiment from real life, right? So I can think that I instantly just bring my system from one hit bar to another hit bar and with this generator. So I suggest okay, so now I'm start philosophizing, yeah, and I'm doing this in the following way. I had certain probability distribution that cannot change instantly, so it's just the same, okay? So magnetic field did not change kind of manifestly because I already kind of consider system included shift by U into shift of the symmetrical. So now magnetization. For magnetization, I have formula. So formula shows that magnetization in principle kind of could change to nu M1 of Q. So from kind of this point to this point, right? But there are very special values of magnetic field when this change does not happen. So let's kind of put warning sign. So this is object of interest. Okay, but if I am not, let's say, here, but in a generic point, so then my initial condition changed. Free energy also changed abruptly. And so then I start flowing with Fokker-Planck because that's the only thing I know. And I will arrive eventually to the kind of distribution, to the Gibbs distribution of the second system. But there could be a remarkable moment corresponding to this point, so very, very special values of Q, where I already, at least in the thermodynamic limit, stand in this Gibbs equilibrium of the second system. So then there is no kind of Fokker-Planck relaxation, at least in the limit, because I'm already in the equilibrium. I will say, okay, so this is the moment of instant relaxation. So that's my model, okay? But on the other hand, I'm saying the following, that from the viewpoint of quantum geometry, this is a moment to become happy, because this
moment what?
to become happy, okay. because this event, right? So this is PQ plane. So exactly means that we have kind of one Legendrian and another Legendrian. So they sit over the same points, kind of QP, and so then rep chord, which is just for us this kind of.
These are for special values of Q.
Oh, absolutely.
Depending upon their temperature.
Yes. So that's for special values of Q. So somehow conclusion which we made, okay, and I challenge physicists to comment about this, that for special values of Q, there exist ultra-fast processes, which kind of, well, happen. Okay, so now, okay, from this point, I can, I already was asked by Gotov, responding about this, so physicists, so whether I've seen such processes in nature. So let's put it in the following way. So I think that there are examples of ultra-fast of ultra-fast processes. Yeah, whether they're described in this way or not, I have no clue. Okay, that's in the future research. Okay.
So you're saying for these values of Q, you're going to equilibrate very, very quickly.
Yes. So that's what I say. Okay. And indeed, kind of, you can make calculation, you can find this red quartz, and you can actually prove by using this interlinking criterion, which I kind of formulated. They are robust, so this means that you can kind of, if you perturb your system, and that's probably the most unclear to me. Where we return when I will go through open problems, kind of, yeah. So. But anyway, I mean, if we have a good way to perturb thermodynamic systems, so then this course should survive. Okay, so right, and so that's basically this formulation of robust interlinking. I want to skip it.
So the small change of your system would be governed by Legendre, by horizontal curves with respect to contact.
Okay, so that classification of thermodynamic process.
Okay.
Yeah, kind of,
Okay.
yeah, to the point. Yeah, so that's what I have to explain. So, okay, well, as I said, so when SNT excluded from thermodynamics phase space, and that's mostly the case, so I assume the temperature is kind of non-decreasing along with processes. So classification of thermodynamic process, that's a little bit of chutzpah, right? So we kind of came up with this, but still, and this is not, I mean, this part is not yet written, so there is some draft. So how one can imagine about thermodynamic process? So I believe that the fact that there are really many descriptions and a lot of literature on various kind of processes is due to the fact that they indeed very much differ. Okay, and they differ first of all by the time scale. So the famous class of processes is quasi-static processes. So it's a family of processes where at each point you can think that you're in equilibrium. Okay, and so for example, so I'm taking this Curie-Weiss and I'm very, very slowly kind of increasing the temperature. Okay, so that's kind of typical example. Okay, so I would model these things by family of Legendrian submanifolds, right? And moreover, these Legendrian submanifolds should be non-negative family because each individual state should go in the direction, that gamma lambda of gamma dot is positive. Okay, so it's exactly a family which we encounter when we speak about partial order. Okay, so there are fast processes, so fast relaxation. So I think that this fast processes is the least controversial kind of class. So that's something which is governed by Fokker-Planck equations. And there are these ultra-fast processes which I described in great detail. Okay, so now if you buy this classification, you can.
Can you go back to that slide?
Yes.
I don't understand the assumption. What is this assumption?
The assumption is the following: that this is so I'm working usually in thermodynamic phase space where T is not a coordinate by a parameter. Okay.
What S and T or what temperature and entropy or what?
Yeah, so there is no entropy and temperature among my coordinates. So, but T is parameter. So one Legendrian for one temperature, another Legendrian for another temperature. It's kind of reduction, some kind of reduction thing. Yeah.
Yeah. No. Can you say what that assumption means? I don't quite understand.
It means you see, thermodynamic phase space is indeed product of human mind. So I can consider or this space or another space. Okay, so I can consider ST as pair of conjugate variables. So then I will work, let's say, Curie-Weiss case in 5-dimensional space. So I will have free energy, magnetization, magnetic field, temperature, and entropy. I will have one Legendrian submanifold. Okay, and so then I have to, I mean, I am interested in perturbing it. but I'm not sure what is a good class of perturbation. So I can change, of course.
You don't want to move those.
Yeah, I don't want, kind of don't want to do it. And I would put it in the following way. Physically, I completely cannot think. Rather, I'm doing the following. I'm chopping this manifold by planes corresponding to constant temperatures. And
But
then,
your dynamics keeps those fixed.
no,
No, okay.
no.
Oh,
So my dynamics does not, I mean, it could keep fixed, but it's not. Okay? And so then we, for instance, arrive to the following question. So I have two submanifolds. So kind of I'm doing a rock thing. Yeah. So instead of writing which temperature corresponds to each of the submanifold, I'm just erasing this. Then I have a process, slow process, which goes from one to another. I'm kind of trying to understand whether, for instance, I can arrive from another to, I mean, whether temperature is remembered at all. Okay. So here are the conclusions. So for me, temperature is a parameter. So here are the conclusions. So if lambda 0 is less or equal than lambda 1, so this means that if I can get from lambda 0 to lambda 1 by a slow process, temperature non-decreasing. Yeah, but temperature is not here. So there is no way that there is a process which takes lambda 1 to lambda 0. That's partial order. And second, if lambda 0 is less or equal than lambda 1, there exists a rep chord from lambda 0 to lambda 1. So in other words, if two equilibrium thermodynamic systems are related by a slow process, so then there is necessarily an ultra-fast process which starts on one system and goes to another system. And that's you already kind of seen in the prologue. Yeah, it's theorem by Weiss and Arlo, right? And another theorem that if lambda 0 and lambda 1 are related to some third manifold by a slow process, so then there exists an ultra-fast in one of the directions. So we don't know in which one necessarily exists. So somehow, I mean, this theory of partial order enables one to relate the slow processes and ultra-fast process. So from contact viewpoint, partial order and chord. Okay, so yeah, and so that's kind of follows from very nice work of the student, Weiss and Arlo. Okay, so now I will probably not.
Yeah, what would that physically mean? There's an ultra-fast process.
Just very fast.
Okay, but what?
I think different. This roughly speaking means that I think physically this means the following: that two systems have approximately, for special values of parameter, have the same Gibbs distribution, so the same equilibrium distribution, which would be kind of for each finite n, also outrageously wrong, but when n goes to infinity, it will be approximate. It will be exactly like this. So this means that for large n, it will be approximately the same. Okay, so that's the.
But there's of course a gap between the slow and the fast. But one understands how that a fast thing gets faster and faster, and then it's
There's a little bit kind of, you see, here is the problem that when something jumps, yeah. So Legendrian in principle goes to a non-Legendrian. So you lose it because it's not the equilibrium. So it's not Legendrian submanifold. Then you kind of a little bit lose the actual connection with contact geometry. So connection appears only this kind of via this chord when this one set intersects. I mean when these two equilibria occurs. Yeah. So I think that interesting question, which is in kind of plans, is the following. So near this chords, you can actually write down for finite n honest Fokker-Planck, and you can try to explore how far kind of how this Fokker-Planck can be approximated by this chord. Okay. Very good. So let me go towards the finish. So I will say just very, very briefly that what is metastability? Metastability, so you remember this picture. Yeah, so this was stable equilibrium, so this is metastable, and this is unstable. So metastable equilibrium is characterized by the following, that if your non-equilibrium process kind of sits in the neighborhood of metastable equilibrium, it spends there a lot of time, okay? And then somehow, but it's not totally stable, because if you shake it, somehow it converges very, very rapidly to a stable equilibrium. And so this is the example which you probably seen, right? So you have ultra cool kind of water, which becomes ice after being shaken, or you can do experiments with your microwave. You are trying to prepare tea in the microwave, yeah, and so if you're doing this wrong, so the water will blow up. Yeah. So that's another example of metastability. So then the miracle I mentioned is the following, that in order to, so from equilibrium thermodynamics, you see this part, kind of, yeah, stable part. But if you want to see metastable part, I mean, this part which you get by analytic continuation, you should reprove, kind of, you should rerun your non-equilibrium process, and you fix the places where the system kind of spends a lot of time, you reconstruct this. Okay, so I want to mention also that in 1963, Glauber suggested a remarkable model of non-equilibrium thermodynamics, which was a Markov chain, okay? And Markov chain kind of converged exactly where it is needed here, and you can write down some difference equation which describes this chain and pass to thermodynamic limit, and then you will get kind of something which is pretty much related to the drift in the Fokker-Planck equation. So limiting dynamics kind of is after diffeomorphism becomes this drift in Fokker-Planck equation. So this is I don't know, it's another absolutely mainstream, super famous model of non-equilibrium thermodynamics, and one of the challenges which we had was to relate it in some way to contact geometry. I think that Senior Schlossman suggested us that should be true. Okay, so let me just conclude. So here is kind of contact glossary for thermodynamics. So just to repeat that contact manifold is thermodynamic phase space, may be reduced. Do not pay attention to certain manifolds. Contact form corresponds to Gibbs fundamental form. Lagrangian submanifolds correspond to equilibrium submanifolds. Non-negative curves, non-equilibrium kind of fast processes. Non-negative passive Legendrians, slow processes, and rep chords correspond to instant relaxation. So that's what I know, I mean, for today. Okay. And here are some open problems. Okay, so first problem, as I mentioned, and I think this is absolutely realistic and should be done. So you can kind of extend this notion of gamma convergence, or kind of Hopper metric Hopper-Shulugin metric convergence, I mean, in the Legendrian settings, and to describe thermodynamic limit accurately, right? So now this naturally yields to the question how to detect chords between non-smooth Legendrians. Because if in the limit we already have this non-smooth Legendrians, we should know how to deal with them. I believe this is probably also quite realistic. So then there is a question I have no clue how to do. So you see, I mean, the chords are remarkable, but if we work with smooth Legendrians, so they can, I mean, we don't have control which states they connect. So if they connect to stable states, we're good. If they connect like metastable with stable or stable with metastable, I can tell you some story, I can cook it. If it includes non-stable states, I am not sure what to say, okay? So rather I would say that, I mean, it's not one-to-one correspondence, but I mean, you should make forthcoming analysis of chords to say, is it indeed an process or not, because of this stability condition, and something should be done with this. So then there is absolutely a kind of scientific fiction question. So as I said, this Fokker-Planck equation is gradient flow generating function, and Cauchy-Riemann equation is gradient flow generating function. And to make this question spicy, we know the generating functions are unique. I mean, when we think about finite dimensional approximation. So somehow, I mean, there might be a connection, there might be no connection, I don't know. And the last question, which I think it's very serious question, and I feel really claustrophobic without this. I want to find the microscopic mechanism of perturbations of equilibrium Legendrians. Okay, so of course, I mean, there is absolutely no problem to perturb Legendrians from the viewpoint of topologists. But then my kind of physically minded friends become very critical and say that, I mean, why God should kind of perturb for you Legendrians, so present some microscopic mechanism. And one of the approaches is reduction of extensive variables. So I may have many unspecified thermodynamic parameters, and this is indeed kind of pretty physical and good. And so then I could declare that certain values are fixed. Okay, so and then you arrive to the kind of form of the Legendrian in the standard kind of form of generating functions. So z equals to f of qx, p equals to d of dq, and y equals to d of dx equal to 0. So if you reduce to 0 value of this extensive variable y, so then you are kind of, you can get non-trivial Legendrians. I don't know interesting physical examples, and that's what we are kind of trying to do. Okay, so thank you.
So you can do all this on compact contact manifold.
Okay, so that's very good question. So I would prefer to do this on jet bundles to compact manifold. Okay, but unfortunately, life brings me very unpleasant conditions at infinity. So that's, roughly speaking, what we are doing. So we work with classes of thermodynamic systems, which kind of behave at infinity in a more or less the same way. So then we make change of variables so that the one system, let's say, becomes zero section and another becomes kind of asymptotic to zero section. So then, okay, so then I can start formulating things. And in order to prove something so far, but I know how to make gluing and reduce it to the case of the circle. So for instance, I mean, existence of this robust chord, the robustness of the chord is proved in this way. Yeah, but that's of course completely mathematical kind of, I mean, tricky, right? So I don't know, I don't know analog of Marsden-Weinstein reduction, which enables one to get from cotangent bundles closed manifold. So could be probably, but I'm not there yet.
So this connects two different things: the Fokker-Planck equation to rate chords.
Yes.
Can I learn something about rate chords? The Fokker-Planck proof of the Weinstein conjecture.
Yeah. So it's indeed kind of very nice question. So using this for contact topology is not yet in the.
I mean, if you're optimistic about 4, then that would indicate that maybe one side is easier to study than the other for certain questions.
Yeah, but look, we're kind of introducing some kind of diffusion into rep flow is not so crazy idea, right? So maybe one can prove something in this way.
Yeah. Einstein conjectures that says there are the super fast things happening, which are periodic.
Yeah, kind of. But even establishing rep chords is interesting.
Yeah.
So not much is known.
You ever see infinitely many records?
Hmm?
You ever see infinitely many records? I know you're in the.
Infinitely many records, not in this setting, not in this setting. They go up.
So you gave the example of the mean field easing.
Yes.
Are there other models that, I mean, it must be much more general.
Yes, so I know, I don't understand how to do it generally, but because I'm not an expert, but I know kind of two other models I'm thinking of. So one model is this liquid vapor ice, right? Where you also have kind of interesting phase transition, you can do things. And moreover, I mean, there you can find example of superfast process even in Wikipedia, like some engines, like this. Okay, and there is example which is extremely interesting to me because after all, I was raised within Hamiltonian dynamics, so it's called Hamiltonian mean field. Okay, so you write down honest Hamiltonian system on a kind of product, or even you can do it on probably symmetric product of cylinders, yeah. So with the potential which is cosine. Okay, and so then you instead of studying dynamics of these things, you are doing thermodynamics. Yeah, kind of studying how this Hamiltonian in thermodynamic limit reacts to changes of magnetic field. Okay, and I absolutely don't understand connection to dynamics.
His connection to what?
To Hamiltonian dynamics.
Uh-huh.
Yeah. So it seems that if I have a Hamiltonian system involving many particles, but that's basically, I mean, this classical guys like Boltzmann, Fermi, so that's they were discussing, right? So they have Hamiltonian system connecting really many particles, right? And so then you can do this contact thermodynamic, but looking at reactions of the systems to parameters, like analog magnetic field, you actually just add it, right? So it's like potential, a system with potential, which is some cosine, I don't know, phi I minus phi j plus u probably b of n, right? Plus q.
This is still mean field now, right?
Yes, it's Newtonian mean field model. Yes, and
That's an XY, that's the XY class.
yeah. And yes, and so then the question which I find interesting, but I would say I'm curious about it, and maybe it's not deep question, whether Hamiltonian dynamics of this Hamiltonian, which we can study by standard kind of rules, yeah, so asking whether you have ergodicity, whether you have whatever dynamic property you want, yeah, so how it's related to thermodynamics.
And so, I mean, you want to replace that one by this continuous one?
Yeah, so this is actual generalization of the Ising model.
Yeah, okay.
Okay.
But it's still mean field.
Yes, it's still mean field. Yeah, right. So
you can solve that. It's soluble.
Yes.
Equilibrium.
Yes. I know that it's solvable. You can do certain things. So yeah.
Dynamics is what you're really interested in.
Yes. So connection to dynamics, I don't understand. Actually, I mean, if this would be, I would be extremely happy. But I absolutely can't catch it.
Now, you've been talking mostly about what I would call first order transitions, right? Because, you know, when you take an Ising model and you're low temperature, you flip the sign of the field from one side to the other, even a small change will flip it all of a sudden, very suddenly. That's what you're talking about mostly.
Yeah.
But then there are second order transitions, which have other kinds of singularities. And I'm just wondering whether they play a role in what you're thinking of.
Which
These are called second order transitions. In other words, you let the magnetic field be zero, but you vary the temperature.
I see.
Then you'll have another transition, but its derivative doesn't jump, but its second derivative does.
I see. No, that's
Or becomes singular.
Yeah, very interesting. And I should say that this idea to increase magnetic field was exactly kind of designed to go away from the singularity.
Yeah.
Because kind of singularity becomes, you know, course which goes from the singular point. I cannot decide. It was kind of resolution of singularity.
You mentioned this result of Leibowitz and Penrose,
Uh-huh.
which tells you that once you have a magnetic field, everything in equilibrium is smooth. Analytic.
I see. Huh. Yeah, I mean, this connection with real analyticity exists kind of long ago. It's not.
Well, if there's no more question, then thanks Leonid again.